Hi everyone, this is Elizabeth Albright, and today we'll be talking about probability and probability rules. The roadmap of the video is first we'll start with frequentist versus subjective probability definitions, and then move on to rules of probability. We'll talk about marginal, joint, and conditional probabilities, and then manipulate these probabilities. And we'll close with a problem to contemplate, and then solve in our next video. Thanks again for joining in. First, we have the definition of frequentist probability. The probability of any outcome of a random phenomenon is the proportion of times the outcome would occur in a very long series of repetitions. For example, if we flipped a coin, a heads-tails coin, 1,000 plus times, we would expect the probability of heads, given more and more flips, would get closer and closer to 0.5, if it is a fair coin, that is. Subjective probability is a measure of the strength of belief about a probability that a specific outcome will occur. This is not based on repeatable events. So for example, what's the probability that Duke will win the women's NCAA basketball tournament in 2021? Or what's the chance that you will get an A in your statistics course? Or what's the probability that the eye of a hurricane will make landfall in North Carolina this hurricane season? But whether frequentist or subjective probability, probability follows a set of rules. The probability that event A occurs sits somewhere between 0 and 1 inclusive. Can be written this way: 0 less than or equal to probability of A less than or equal to 1. And we know that the sum of the probabilities of all potential outcomes is 1. A definition here: the probability of the complement of event A, or not event A, can be written as probability not A with a line over it. And probability A plus probability not A equals 1. We can talk about disjoint, or what we call mutually exclusive events. So if A and B are two disjoint events or mutually exclusive events, then probability A and probability B each range from 0 to 1, as we stated before. And probability of either A or B equals the probability of A plus the probability of B. Probability of A or B equals probability of A plus probability of B if they are mutually exclusive events. Another way to write this is probability of A union B equals probability of A plus probability of B. Again, under the assumption of mutually exclusive events. So as an example, what is the probability of rolling one 6-sided die and getting a 3 or a 4? We know that they are disjoint events. You can't roll a 3 and a 4. So probability of 3 or 4 equals the probability of 3 plus the probability of 4. And this equals 1/6 plus 1/6, which equals 2/6, which equals a third. So now let's talk about marginal, joint, and conditional probabilities. Marginal probabilities is what we have been talking about: probability of A or probability of B. We also have conditional probabilities: probability of A given B. And we have joint probabilities: probability of A and B. And joint probability of A and B can be written as the intersection of A and B, as denoted there, with the upside down U. Conditional probability: What is this? Conditional probability is the set of relevant outcomes is restricted by a condition. Example, probability that it will rain today given that it rained yesterday. The condition is it rained yesterday. Conditional probability is denoted probability of A given B, as I stated in the last slide. And then we have a multiplication rule here. Or, in other words, joint probabilities equals marginal times the conditional. The probability that events A and B both occur, that intersection of A and B, equals the probability of A times the probability of B given that A occurred. So an example or a problem here. You have a bag of 9 tiles numbered 1 through 9. What is the chance that you will pull 2 odd tiles without replacement? You will pull one and then pull another without putting the first one back. So go ahead and stop the video and do a quick calculation and then come back, please. Thank you for coming back. Shuffling the tiles. And we pull a 3. We can count the number of odd tiles out of the 9. 9, 5, 7, 3, 1. And so the probability of odd on our first pull is 5 out of 9. We keep the 3 out, reshuffle the tiles, and pull another one. And this is probability of odd on pull 1 and odd on pull 2 equals the probability of odd on pull 1 times the probability of odd on pull 2 given that we pulled odd on the first pull. So we pulled a 5. We know that the probability of odd 1 equals 5 out of 9, 5/9. We didn't put that one back, so there are now 8 tiles with 4 remaining odd tiles. So we have 5/9 times 4/8 equals 2072 or 5/18. We could also calculate a decimal. I was being a little lazy. Again, the joint is the marginal times the conditional. Conditioned on that marginal. The addition rule. Assume there are 2 events and we want to know if either event occurs. We are not assuming that these events are disjoint, as we talked about earlier, or mutually exclusive. We are not assuming mutual exclusivity. We know that probability of A and probability B both lie in the range of 0 and 1, inclusive. And A union B equals probability of A plus probability B minus the intersection of A and B. So let's think about this, and this time we'll use the example of a French deck of cards. Deck of cards is composed of 52 cards made up of 4 suits: spades, clubs, hearts, and diamonds. 2 of those suits, spades and clubs, are black, hearts and diamonds are red. And each suit has 13 cards each. We pull one deck one card from a deck of 52 cards, the deck that I just described. What is the chance that the card we just pulled is red or an 8? So again, we pull one card from the deck of 52 cards. What is the chance that it is red or an 8? Please go ahead and stop the video and do the math. So we can write this as the probability of red union 8 equals the probability of red plus the probability of 8 minus the intersection of red and 8. So probability of red union 8, or red or 8, equals 26 out of 52 plus 4 out of 52 minus 2 out of 52. That gives us 28 out of 52, or roughly 53.8% probability. As background to the final problem of this video, I'd like to introduce you to the Albemarle-Pamlico Estuarine system. This estuarine system is the second largest in the United States, second to the Chesapeake Bay, and spans over 3,000 square miles. As you can see, the waters here drain from several river basins across the eastern portion, or what we call the coastal plain of North Carolina, and southeastern Virginia. The estuarine systems in North Carolina support a diversity of shellfish, some of which are harvested for human consumption. To ensure the safety of the shellfish for human consumption, the North Carolina Department of Environmental Quality monitors the waters for the presence of bacteria. If levels are found to be high, a shellfish harvesting area is closed. It is illegal to harvest shellfish from closed areas. As you see in the map, shellfish harvesting areas are delineated by the hashed lines. Open areas are in blue, and areas in red are closed. The next slide presents the final problem for this video. Please list all the probabilities mentioned in the problem and state whether they are joint, marginal, or conditional probabilities. Be sure to identify the probability that the question asks you to solve. If you are feeling motivated, see if you can solve the problem through manipulating the probabilities. We will work through the problem in the next video. The numbers presented in this slide are an illustrative example and should not be taken as an accurate portrayal of North Carolina estuarine waters. So here is the final problem. Fecal indicator bacteria, or FIB, such as fecal coliforms and E. coli, are used as an indicator of fecal contamination in water. These indicate the potential presence of harmful waterborne pathogens that can affect human health, especially in shellfish harvesting estuaries. Field studies have estimated that harmful concentration of FIBs, in other words, above the state water quality standard, are present in 10% of North Carolina shellfish harvesting areas. If concentrations of FIB exceed the water quality standard, the North Carolina Department of Environmental Quality will close an area for shellfish harvesting. It is illegal to harvest shellfish in a closed area. Scientists estimate that if an area has FIB concentration levels above the state standard, there is a 75% probability that shellfish in the area are contaminated. If measured FIB concentrations are less than the state water quality standard, there's a 5% chance that shellfish harvest will be contaminated. If a fisher harvests contaminated shellfish, what is the probability that the harvest occurred in an area with high levels of FIB? In other words, above the state standard. And please remember, this is an illustrative example and does not necessarily represent the true status of North Carolina water. Please stop the video and write down the probabilities that are presented in the problem. Thank you for rejoining. I will now go over the probabilities that were given in the problem. I broke up the probabilities into marginal and conditional probabilities. The probability that FIB exceeds the standard was given as 0.1. We could easily calculate the complement of 0.9, or the probability that FIB does not exceed the standard. There were also conditional probabilities given in the problem. For example, the probability of given fib exceeds the standard that shellfish is contaminated, and that conditional probability was given as 0.75. From that, we also then know that the probability given fib exceeds the standard, the probability that shellfish will not be contaminated, is 0.25. Another conditional probability that was given in the problem was given fib does not exceed the standard, the probability that shellfish is contaminated is 0.05. From that, we can calculate its complement. Given fib does not exceed the standard, the probability that shellfish is not contaminated is 0.95. So what is the question asking? It's asking, if shellfish is contaminated, what's the probability that the fib in that area exceeds the standard? This is a conditional probability, but was not given in the problem. But we can solve it with the probabilities given in the problem. To do so, we need to manipulate the joint, marginal, and conditional probabilities using Bayes' theorem. This is easy to do. We will go over this in our next video when we go over probability trees. Thank you for joining in for today's probability lesson. Again, this is Probability Rules and Marginal Joint Conditional Probabilities with Elizabeth Albright of the Nicholas School of the Environment. Thank you again for tuning in.